I'm delighted to come talk to you about the exploration of Mercury and a project that has been going now for about 11 years. I'd also like to acknowledge that the man who got me into the field of geophysics is sitting in this audience, who gave me my first geophysics class as a sophomore at Caltech. Thank you. Just a few facts to bring everybody up to speed on the planet Mercury, which of course is one of the sister inner planets to our Earth. But it is the smallest, the inner planets, and the last 3 years has been the smallest planet. But we think that all of the inner planets formed at about the same time by the same processes, and therefore studying all of them as a group informs us much more about our own home planet than studying one planet at a time. Mercury is only 5% of an Earth mass, but it is very dense. It's got the same bulk density as the Earth, from which we infer that Mercury is mostly iron metal. It's got a core that's at least 60% of its mass. For reference, the Earth's core is only 30%. And Mercury is the only inner planet other than Earth that has its own global magnetic field. And a big mystery is why such a small planet still has a global magnetic field. But because most of Mercury, here's a possible model for what Mercury might look like inside, most of it is iron metal. Some of it is molten, some of it may be solid. But the silicate shell, or rock, that surrounds that core is at most 600 kilometers thick. It's not very thick. In contrast, the Earth's core is nearly 3,000 kilometers below the surface. So one is already much closer to the core of Mercury, at Mercury's surface than we can ever be at Earth. The only spacecraft, private messenger, to visit Mercury was one in the Mariner series, Mariner 10, the last in the series, which was launched in 1973 and encountered Mercury 3 times, flying by at intervals 6 months apart, and taught us much of what we know about Mercury. And here's a very short list of what Mariner 10 taught us. Mariner 10 saw the same side of Mercury in sunlight at each encounter, so it imaged only about half the surface, a little less. It discovered Mercury's global magnetic field. It detected the first 3 species in Mercury's atmosphere. And the technical term for the very tenuous atmosphere that Mercury has is an exosphere. An exosphere is an atmosphere where the density is so low that the individual atoms don't know they have neighbors. They don't collide. They just follow trajectories governed by their temperature and the gravity field that's holding them to the planet. And Mercury, by virtue of having a magnetic field, has an envelope of space in which that magnetic field is dominant, called the magnetosphere, as does the Earth. Is protecting us even now from charged particles from the sun and from the galaxy. And Mercury has such a magnetosphere, but it's tiny and it's extremely time variable. So that's what Mariner 10 taught us. Earth-based astronomy gave us the rest of what we knew about Mercury prior to the Messenger mission, and here's an abbreviated list. It was Earth-based radar that taught us that Mercury is in what's called a spin-orbit resonance, meaning that there's a commensurability between the day and the year, the spin rate and the revolution around the sun or around the primary. The most common spin-orbit resonance in the solar system is called 1-to-1 spin-orbit resonance or synchronous rotation. The Earth's moon is in synchronous rotation, and that's why we see the same face of the moon to within a few degrees at all times. And that's the front side and the back side. Mercury's resonance is 3-2. 3 days equals 2 years. That's very unusual. We don't know any other solar system body with that spin-orbit resonance. It means that the solar day on Mercury, the time it takes for the sun to go through 2 successive passages overhead, is 2 Mercury years, about 6 months or time. Earth-based astronomers discovered other species in Mercury's atmosphere, including sodium, potassium, and calcium. These are somewhat unusual species for a planetary atmosphere. These must be derived from Mercury's surface. They're too abundant to come from the sun. We'll come back to that topic. Earth-based radar discovered almost 20 years ago that Mercury has polar deposits. And here's an image of Mercury's polar deposits at one pole. These are radar-bright materials that have a radar backscatter and a radar depolarization that is best matched in the solar system by only one material, water ice. And it's somewhat paradoxical that the planet closest to the sun might have water ice at the poles. And the reason is that the spin axis of Mercury is almost perpendicular to its orbital plane. And areas that are topographically low, like impact craters, at the poles, never see the sun. They're in permanent shadow. And because the atmosphere is so thin, there's no transport of heat from the planet's equator to the poles, like occurs on Earth. And so the regions of permanent shadow look out into black space. They're extremely cold, much colder than the freezing point of ice. And if there's a way to get water to the surface of Mercury, some of that water will find itself in these permanently shadowed polar crater floors. So that's the hypothesis to explain the radar data, but we'd like to test that with messages. And finally, radar discovered 3 years ago by an argument having to do with a variation in the rotation over a Mercury year, that Mercury's outer core, like that of the Earth, must be cold. Just a brief word about NASA's Discovery program of small competed missions, one of which was led by Don Brownlee, the Stardust mission. It's had a wonderful success. Don's in this audience. These are missions that are competed every few years, constrained by cost, by schedule, and by launch vehicle, but otherwise open to the community to propose interesting ideas that must be scientifically challenging and technically not challenging. It must be technically ready and feasible. And it's produced these first 10 missions that you see here, plus the Grail mission, which post-dates this slide. But what is unusual for NASA about these missions is that they're led by a scientist, a professor at the University of Washington, or a scientist at the Carnegie Institution, rather than a NASA center. And they all must have ambitious goals, and the goals of the Messenger mission was to answer these questions. How did Mercury end up so dense? That goes back to the planet-forming process. What is the geological history of Mercury, and how does that compare to its sister inner planets, including Earth and Venus and Mars? Why does Mercury have a magnetic field and Mars and Venus don't, but the Earth does? And what has that got to do with the structure of Mercury's core and how much of it is molten? Are the radar reflective materials at the poles indeed water ice? And what's happening with this very dynamic exosphere and volatile species in general this close to the sun? Well, the argument we made was that not only are these questions important for Mercury, but they tell us about the family of all the inner planets, if we can answer them, and that these questions are capable of being answered by instruments that we place in orbit around Mercury. That was the argument. They bought the argument at NASA, and they bought the spacecraft. But there's a reason why no spacecraft has ever orbited Mercury before, and that's because it faces two major technical challenges. Start taking notes. And they are depicted by this image of Mercury transiting the sun, which it does with great frequency every decade or so, unevenly spaced. This is 2003. It is a very small object by comparison to a very hot object nearby. And as a result, it is a challenge dynamically in terms of celestial mechanics to go and send a spacecraft from the Earth toward the sun and go into orbit around an object only 5% of the Earth's mass. That requires a big change in the spacecraft speed, what the spacecraft engineers call delta V. How much you have to change the velocity of the spacecraft relative to your target to be captured into orbit. And for Mercury, that's like 10 kilometers a second. That would be the speed that the spacecraft would have flying on a direct planetary transfer orbit from the Earth to Mercury if you did nothing else but allow Newton's laws to follow their inevitable conclusion. And so you've got to come up with some way. We don't have anywhere near a propulsion system that can do this change in a single burn. Some way to solve this problem. And the other problem is the sun is, of course, very hot. And so the environment at Mercury is a big challenge to thermal design of spacecraft that depend on electronics, certainly silicon-based electronics, which don't operate very well at temperatures this close to the sun. So that's the second challenge that must be met. And prior to Messenger, no spacecraft concept had adequately solved these problems. how does messenger solve them? With a variety of ways, and I won't go into all of them here, but to some extent the spacecraft addresses both challenges. It addresses the thermal challenge of the sun by pointing a sunshade at the sun at all times. That sunshade is made out of ceramic cloth with some multi-layers of insulation behind it, and is pointed at the sun at all times. The solar rays take advantage of being close to the sun, but have to operate at control temperatures, and so it uses mirrors and articulation to control that temperature. In order to get the high delta V, the spacecraft required all dry mass on the spacecraft had to be reduced to low values, and that was done through very thoughtful integration of the propulsion system and the structure from an early stage, choosing materials that were low in mass and reducing mass wherever possible. The communication system itself is low mass and based on an electronically steerable phased array without movable parts. The mission design addressed the need for this large delta V, for changing the velocity of the spacecraft enough so that the propulsion system we can carry can do orbit insertion. Now this is a pretty complicated diagram. It's looking down from the North Pole of the plane of the Earth and most of the other planets at the trajectory that MESSENGER takes from launch to orbit insertion. And what you see is that there are many, many orbits around the Sun, 15. Here's a timeline at the bottom going from launch to orbit insertion. That's 6.6 years, with some milestones along the way. And those are critical. There are two kinds. There's ones that look like a planet, and there are these triangles. The triangles are planned major propulsive events, changing the trajectory of the spacecraft and targeting it for the next planetary flyby. And the planet symbol denote the fact that the spacecraft flew by first Earth and then Venus twice and then Mercury 3 times, using each of these flybys to change the trajectory in a way that brought the relative velocity of the spacecraft closer and closer to a small enough number relative to Mercury that our propulsion system could do orbit insertion. So each of these flybys was an opportunity for science, but it was absolutely critical for getting into orbit around Mercury. And right now we're about here on this timeline. We've had all 6 flybys, all 5 planetary events, and we're looking forward to orbit insertion around Mercury in about 11 months. But without this very clever mission design, we could not have done an orbital mission. These kinds of techniques have been known for maybe 25 years, but this is the first time they're being put into effect for a Mercury orbiter. Here's a summary of some testing we did to validate the thermal design, and in particular, all of the components that had to operate facing the sun. This is a small portion of sunshade material with a high-gain antenna and some other devices that had to see through the sunshade. Taken to a big vacuum chamber at NASA Glenn in Cleveland and subjected with temperature measured to increasing intensity, simulating proximity to the sun, and measured in number of suns, where one sun is what you see from orbit around the Earth, and 11 suns is what you see at Mercury when it is closest to the sun at perihelion. And here you see the validation of the thermal design and the testing. The front of the shade ramps up at 11 suns to a temperature of about 350 degrees centigrade. That would fry any of the electronics on our spacecraft. The back of the shade down here is almost insensitive to solar illumination on the front side. It's room temperature. So this was an excellent design. It is a challenge to the spacecraft to keep the sunshade pointed at the sun at all times. That's another topic, but the sunshade itself does its job. It did it in Cleveland, and it does it around the sun today. We carry 7 scientific instruments that are designed to answer the questions that frame the mission. Some of these have multiple components. They're illustrated here. There's an imaging system that has a scan platform that gives it another degree of freedom in pointing. But every other instrument is mounted in a fixed manner to the spacecraft. And if you want to look in a different direction, you turn the spacecraft. Substitute a constraint that the sunshade must always be between the sun and the spacecraft. So what else is aboard? There are two devices that are elemental remote sensing. One looking at gamma rays, both naturally emitted and ones that are stimulated by the interaction of cosmic rays with materials on the surface of Mercury and are generated there at specific energies, diagnostic of individual elements that are major rock-forming elements. There's an X-ray spectrometer that looks at X-rays excited by solar X-radiation, again, that come off the surface at energies that are diagnostic of specific elements there. That is to say, when the sun is active at X-ray wavelengths. There's a laser altimeter that will look at topography of the shape of the planet and also the response of the planet to variations of solar torque during its orbit. There's a magnetometer. There it is. That's at the end of the 3.5-meter boom to get it away from what is already a magnetically quiet spacecraft. There are two energetic particle spectrometers, one at high energies, one at plasma energies. And there's a remarkable double-duty, very high spectral resolution spectrometer that looks at the atmosphere, where there are emission lines diagnostic of individual species in the atmosphere, and of the surface, looking for mineralogical absorption features in the surface reflected from the ultraviolet through the very near infrared. We, of course, launched. If you ever have a chance to go to a launch at Cape Kennedy, take advantage of the invitation. A nighttime launch, even of a Delta II, much less something like a space shuttle, is absolutely terrific. And of course, if you've got a spacecraft aboard, it's a very warm feeling to see a successful launch. This is a depiction of the 3 flybys. 2 of them were in 2008, and one was September last year. Remember that these flybys were necessary so that we can do the orbit insertion next year in March of 2011, but we were able to accomplish a great deal of science at each of these flybys. They all go from left to right. There's Mercury looking down from the North Pole. The side facing the sun is shown in sort of daylight. There's the terminator. The closest approach was 200 kilometers in all cases, always on the night side. So we're approaching from the anti-sunward direction up the magnetic scale. And we're looking back at the mostly sunlit surface as we depart from each of these encounters. And we saw almost opposite hemispheres illuminated in these first 2 flybys. So we've seen a lot of the planets just from these flybys, and we've utilized all of the instruments aboard. And I'll talk about some of the results from these flyby measurements as we look ahead to orbit insertion. This is our first approach, put together as an animation. This was really an exciting time. It's been the first time a spacecraft has visited Mercury in almost 33 years. We were able to carry instruments that hadn't been invented or sharpened in their capabilities in over 3 decades of technology. And so we were able to measure a lot of things for the first time. All of the flybys worked well, not equally well, particularly the 3rd flyby, where we did have a safe hole. But they all worked well in terms of returning large data sets, a lot of images, and a lot of data from all of the instruments aboard. And as a result, we were able to do a lot of things for the first time at Mercury. I won't read these, but you can see examples in terms of closest approach, in terms of the first spacecraft observations of what I will describe in a minute, Mercury's neutral tail, comet-like tail. First measurement of plasma ions in the magnetosphere, laser altimetry, imaging, spectroscopy, etc. If you visit a planet for the first time in over 3 decades, there's lots of things you can do for the first time. Okay, results. Let me say a few words about the magnetic field of Mercury. Remember that Mercury is the only inner planet other than Earth to have a magnetic field. We don't yet know why, but one of the ways to get at this question is to measure the geometry of the field. Here you see, looking down on the North Pole of the planet, are the passes that Mariner 10 made. There were 2 inside the envelope that is dominated by Mercury's magnetic field, the magnetosphere, and the first 2 flybys by Messenger. And what was important is that they were on opposite sides of the planet. And so they allowed us for the first time to see something about how symmetric the field was as a function of longitude. And here you see some depictions of total field strength. The spacecraft came in from the left, got inside the volume of space dominated by Mercury's magnetic field, and saw the magnetic field of the planet. We looked, by the way, for strongly magnetized portions of the crust. Those have been seen on Mars at very high altitudes. They can be seen from Earth orbit for some continental scale magnetic anomalies. So far, we haven't seen any at Mercury. We will be looking. This is a way that magnetic field scientists display the solution for what the geometry of the field is. And it's a little arcane for those who are not in the field. This is the geometry of the total field at the uniform altitude above the surface of 200 kilometers. This is the geometry of the component of the field that points outward, the radial component, at the core mantle boundary. And what you look for is one color in the north and one color in the south, and that's the field of a dipole, the field of a bar magnet, a large one, at the center of the planet. And what you can see is that to first order, Mercury's magnetic field is that of a bar magnet, a dipole, that's aligned with the spin axis. But there are some important variations, and you can pretty see them here, variations in longitude, and differences in the two hemispheres that indicate that there are other components of the magnetic field, what the magnetic field people call higher order components, that are telling us something about the source of the field. But the fact that we saw no crustal magnetic anomalies to date, that the field is dominantly that of a dipole, that it strongly aligns with the spin axis, are all votes in favor of Mercury's magnetic field being generated more or less like that of the Earth by convective motions in the electrically conducting fluid metal core. So we think that this is a magnetic field generated by what's called a dynamo, albeit one that produces a much weaker field than on Earth, analogous to that in Earth, but probably with some important differences we hope to resolve with measurements made from orbit. It's just a message that it's a complicated business. In the absence of the sun and the stream of charged particles, plasma, that leaves the sun at all times, the solar wind, and the magnetic field, the interplanetary magnetic field carried by that solar wind, the magnetic field of Mercury might look like this. Dominantly dipolar field lines that go from one pole to the other. Nice geometry. You can figure this out easily from orbit. But the real field lines look something like this. They're strongly influenced by the solar wind, and that solar wind and the field that goes along with it changes in ways that have a dramatic response at Mercury's magnetosphere. And so the challenge to understanding the internal field is to separate out the time variable dynamic components of the field from those that are steady and arising from the interior. The challenge to understanding the time variable part is to understand Mercury's magnetospheric dynamics, all of the current systems there, and quantitatively how those structures and current systems change in response to solar wind conditions. It's a wonderful laboratory for studying magnetic fields and magnetospheres that are broadly Earth-like, but have some very, very important differences, and we look forward to those efforts as we go into orbit. So broadly, the magnetic field is that of a dipole. It's well matched to both the Mariner 10 and Messenger observations, and so far we see nothing in the way of crustal anomalies. Now turning to the exosphere. The exosphere is this very tenuous atmosphere, and it's made up mostly it's got hydrogen and helium from the solar wind, but mostly it's heavy atoms that have been removed from the surface of Mercury and are still influenced by Mercury's gravitational field. On the left is a cartoon of some of the processes thought to be important for moving atoms from the surface into the exosphere. Sunlight and heat from the sun, direct impact of the surface by ions, say from the solar wind or from the magnetosphere, and direct impact of the surface by dust particles and small meteorites, all of which are capable of freeing material from the surface to the exosphere. And then the particles, remember they don't collide, follow ballistic trajectories, and if they have high enough energies, they get high above the planet. If they don't, they come back down somewhere else on the planet. Well, if they're high enough, They're also influenced by sunlight, by the pressure of solar radiation. And that solar radiation pressure can push these energetic atoms away from the sun and in the anti-sunward direction. And they leave the gravitational field of Mercury and they form a comet-like tail. So let me show you what that tail looks like. We carried a high spectral resolution spectrometer. Remember, it's tied to the, it's fixed to the spacecraft. And it's supposed to start and then hit. So I think you can't see me staring you over here. As we flew in, this one from the first flyby, these are individual spot measurements of the column intensity of emission at one of the lines of sodium. These lines are excited by sunlight and then re-emitted as a scattering phenomenon. And the sun direction is to the left, and this is the tail direction. These observations can then be contoured, and you have a map of the intensity of sodium emission with some line of sight influence on the numbers in the near planet part of this tail. This tail has been seen from Earth to extend at least 1,000 planetary radius. So it's a big phenomenon, much like comet tails. On the second flyby, we made observations of this tail in other wavelengths, diagnostic of calcium, which has been seen from Earth, and in a search for another species that can't be seen from Earth because its emission is in the ultraviolet, where the atmosphere gets in the way. But these species show that they're there in the tail, but they have a different distribution with latitude and distance, indicating that there's a mix of source processes that's giving rise to this different geometry for these different species, suggesting that there's a rich opportunity to understand all of these processes by looking at multiple species and different times. And one hint that time matters is this comparative plot of the sodium tail during the second flyby and the third flyby, plotted on the same scale. The sodium tail is almost invisible here. It's down by a factor of about 20. And it has to do with the greater distance that Mercury was from the sun and the different speed that Mercury was making relative to particles and radiation from the sun at this position relative to this position. So the excitation of emission was different in this setting, and it speaks to the strong variations that can be expected during the Mercury year. And what we're looking forward to is being at Mercury, taking these kinds of snapshots of what's going on in the atmosphere throughout a Mercury year, at different times of day, and different levels of activity in the sun. We were also able to measure ionized particles in Mercury's atmosphere. In this cartoon view of Mercury's trajectory on its first flyby through the magnetosphere of Mercury, produced by colleagues at the University of Michigan, shows the geometry at top and shows you two plots of plasma ions at the bottom. The top plot are solar wind plasma, dominantly protons, and the bottom plot are heavy ions, dominantly singly ionized sodium. And you see that particularly the protons are seen throughout the magnetosphere as the spacecraft traverses the magnetosphere. And you see some peaks in the heavy ions, particularly at one of the magnetospheric boundaries and the closest approach. Well, these kinds of data are a rich source of information on interaction of Mercury with the solar wind and on those components of the exosphere that have become ionized by ultraviolet and other processes that are also telling us about material coming from Mercury's surface. This is an early spectrum from the first flyby of ions cast in terms of mass per charge from a time of flight component on one of the energetic particle spectrometers or plasma energy, and a fit to a particular set of spectra showing peaks for sodium and silicon and other species that are well fitted to this particular zone spectrum through Mercury's magnetosphere, telling us that this is a way, as we get better statistics and more time inside the magnetosphere, that we will be able to make an inventory of the charged species throughout Mercury's exosphere and magnetosphere. Mercury Messenger operated its altimeter during the two of the first three flybys. Here you see an altimetric profile from the very first flyby, 5 kilometers of topographic range, and a lot of short wavelength features, some of which then we only had for comparison this Arecibo radar image that we've since imaged with our own imaging system. And features like these are impact craters, and we can determine depths, and we've also overflow tectonic features, faults. I'll talk to a couple of those later. This just shows that we've now built up images for regions around the two profiles we have from altitude. This is the coverage of images. We now have imaged with Messenger more than 80% of the planet, nearly 90%. And when you throw in the images from Mariner 10 showing green, 98% of Mercury has been imaged. Everything except some of the regions close to the pole. Now, it hasn't been evenly imaged in terms of lighting or resolution, but we know most of what's on Mercury's surface at some level. And this is a very important knowledge as we head into orbit. A few words about color, because now I'm going to talk about the imaging that we've done. Mercury is pretty gray, and this is an image looking back at Mercury after the first flyby, at close to what your eye would see had you been on the spacecraft. And those of you with sharp vision, color acuity, and sitting in the front row can tell that these features are a little bluer than the others, and this area here a little redder than yours. But these are all digital data, and they can be enhanced by image processing methods. My colleagues on the image processing team addressed the question of how many types of units can you see on the surface of Mercury on the basis of color and brightness. And the answer from the first flyby was 6. They're listed here, you don't need to know their names. But that means that all of the areas that were imaged during that first flyby fall into one of 6 groups on the basis of color, meaning the slope of the reflectance spectrum, and overall brightness, or average reflectance. And we think these variations mean differences in composition, and we think that areas that have the same color and brightness are approximately the same composition. But at this stage, we don't have chemical information. That will have to come when we go into orbit. A different way of projecting the same information, different choices of colors, now comparing the first flyby and the second flyby, shows that the color units are about the same. That the groupings that we needed to characterize all the regions seen in the first flyby were adequate to describe everything we saw in color and brightness in the second flyby. So from that point of view, the two halves of Mercury are about the same. A little bit more on what these features mean. Of course, we have high-resolution spectra of many areas on the surface. They all look something like this. This is now going from ultraviolet wavelengths to near-infrared wavelengths. This is the ratio of the brightness of Mercury to the brightness of the sun, or the reflectance. But these curves are very, very smooth. And for comparison, you see some plots from the moon and from some asteroids that show absorption bands, places where the reflectance has a local minimum. And those are due to mineralogical effects that are diagnostic, depending on the wavelength, of particular minerals on the surface. So for instance, we know that all of these features are due to absorption in silicates that contain some iron, some ferric iron. And even in the lunar highlands, this Apollo 16 site, you can see this band, although it's very, very weak. Well, this band is not seen at Mercury, and none of the spectra we have obtained shows that this is a mineralogical absorption feature. So unlike the moon and most asteroids and most planetary surfaces that have hard surfaces, there's not much iron in the silicates of Mercury. I'll come back to that. I want to talk about volcanism next. I want to start with this type area. This is the large impact feature called caloric, half of which was imaged before by Mariner 10, but this area was in darkness. We filled it in with Messenger, showed it to be a somewhat larger feature. It is the largest well-preserved impact feature on Mercury at about 1,500 kilometers in diameter. But I don't just show it for itself alone. It turns out to be a region that's extraordinarily interesting from the point of view of the later evolution of the planet after the Basin was put there. First of all, there's an important difference that shows up in spectra and color of plains units. These are smooth areas, both inside the basin, high reflectance red plains, and surrounding the basin on the outside, low reflectance blue plains. These are all very smooth, and implying that they're deposits of very low viscosity materials. But the inside material is brighter and redder, more cheaply sloped than the outside material. So we think that they're different compositions. Here you see the range of reflectance for different types of areas on Mercury, including the global mean. And what's important is not so much that they're different in composition, because we don't know what that composition means, but they're also different in age. And they're different in age from the basin itself. And that's determined on Mercury not because we have any samples that we can date in the laboratory, but on the basis of the density of impact craters that have accumulated on the surface. The longer a surface has been around, the more craters it should have, because craters are pretty random, they hit all parts of the planet. And these are plots with some information removed of the density of impact craters. And the red and the green here compare the planes inside and outside. And they're pretty close to each other. If anything, the inside planes have a few more craters than the outside planes. But here's a comparison between the outside planes and the basin itself, as measured by craters on the rim of the basin. And what you see is for these craters 150, 200 kilometers in diameter, there's a lot more of them per area on the basin rim than there are on the plains. So the plains are younger than the basin. We don't know by the amount, but we know it's resolvably younger, meaning that they're not related to the basin of its formation, and they're plains, so they're most likely the remnants of volcanic eruptions, very fluid volcanic eruptions that occurred after, well after, the basin itself formed. But there's some other evidence for volcanic origin. Surrounding Caloris are these reddish areas, diffuse red spots, two different versions of the same color information. Here is one of these red spots in a high resolution image. It's got an irregular depression. It's surrounded by bright material. It's here on this large plot. These diffuse deposits overlie older crater-formed deposits, in some cases all the way up to the rim of those craters. There's an apparent slope away from the center and down. Here you see the scale. The best analog to this kind of feature anywhere in the solar system are these lunar Mare domes. And closer to the scale, the center irregular depression, the distinctive color of the deposits around them. These are sources of volcanic eruptions on the moon, and moreover, they're sources of pyroclastic, or explosive volcanic eruptions, and I'll come back to the importance of that intro. But this is the volcanic center, the first clearly identified on Mercury. Not necessarily the center for all of the plains inside Caloris, but a distinct center of volcanic eruptions. And if you look at the other diffuse red spots around Caloris, you see that they share many characteristics in terms of the central irregular depression and distinctive color and boundaries that are irregular and diffuse. Now, why is that important? It is important because it says something about how Mercury was assembled. Explosive volcanic eruptions on Earth, and it is thought on the Moon and on Mars, require that the eruptive magmas have some volatile material. It might be water, it might be a carbon dioxide or monoxide, it might be some other species. But that volatile species comes out of solution with the magma rises and goes to lower pressures. And if that volatile is trapped in the magma, it can drive conditions toward ones that favor explosive eruptions. And the expectation was that Mercury would not have a lot of volatiles inside, that it was born of high temperature processes peculiar to conditions very near the sun, and ones that gave rise to an unusual bulk composition for the planet, one that was dominated by an iron core. So we didn't know much about volatiles before Messenger. We did know that Mercury has an exosphere that has species like sodium and potassium that aren't expected to be in abundance in the inner solar system because they're volatile species. We've also now flown through Mercury's ionized exosphere and seen species indicative of volatile. But of course, that just speaks to the surface of Mercury and the source of the exosphere and not to what's inside. We also know that the outer core of Mercury is molten, and we know that a completely iron core would have solidified over the history of the solar system on the basis of theory. So there ought to be a light element, and maybe it's a volatile element. Sulfur is a candidate because it's commonly thought to be important to the Earth's outer core. But this indication that Mercury has pyroclastic eruption, explosive volcanic eruption, puts the finger in at least these locations, that there must be water or some other volatile that was at depth at the time these magmas were formed by melting of subsurface silicate. And so that requires that however Mercury was formed, that some volatiles were left inside. So that was an important result. Just one other comment on volcanism comes from altimetry. You see a comparison of two impact craters next to each other. One of them with a very deep floor. One of them you can barely see in the altimetry because it's been completely flooded. Right next to each other, same diameter, very different profiles from the altimetry. The volcanic, mostly volcanic, we can't say they all are volcanic, but the plains on Mercury are areally and volumetrically very important. They cover at least 40% of the surface. We know in many cases they are volcanic. We know on the basis of spectral information they can be several kilometers thick. They span the range of colors seen on the surface. And where we can make a case on the basis of crater density or particular landforms, most of these plains are volcanic. So it says that at least 40% of the planet, give or take some uncertainty, has a volcanic origin. We learned from the third flyby that there are portions of Mercury we've seen for the first time last fall that are telling us new things about the volcanic history. This bright area with an irregular depression in the middle, we don't have very high resolution information yet. We will from orbit. Is a candidate for being the largest expanse of pyroclastic deposits on the planet. We'll see if that's the right answer. This basin was seen for the first time. The center of it is extraordinarily smooth. It's distinct in color from its surroundings. It's almost no impact crater. This itself is a fairly young two-ring basin, almost 300 kilometers in diameter. But the central plains have to be volcanic because they're younger than the basin in which they lie, and they're different in composition, and they have almost no craters, meaning that we're looking at what may be the youngest volcanic deposit seen so far on Mercury, and that's just from the third flyby. A few words on faults, and then I'll bring this to a close. Most of the faults on Mercury are contraction. They reflect shortening of the crust, and these contractional faults are everywhere. They were seen from Mariner 10. They were predicted to be seen everywhere from Messenger. We've seen them. And what this means is in order to get contraction everywhere, you've got to have the planet shrink. So Mercury is the incredible shrinking planet. The evidence are these global systems of huge faults, some of which are kilometers high. Here's an example of why we think they're contraction. There are many now examples where there are impact craters that predate the tectonic activity. If you look in detail, here is that scarp. There's only half of that crater left because this side of the fault has moved up and over the other half of this crater. So this crater predated it, used to be round, half of it's missing because the entire crust has been shortened. And for a variety of reasons that I don't have time to go into, the amount of shrinkage is growing as we come up with better ways of estimating the shortening across individual faults and are able to see faults for the first time that expand the range of those features. It's also intriguing that some of the most highly deformed areas on Mercury are the centers of great impact basins, indicating that the basin came along and blasted a big hole in the planet, filled it up in some cases partly with volcanic deposits, but then became a focus for continued activity, including deformation, that gave rise to some of the most spectacular fault-type structures that we see today, including most of the extensional deformation, the destruction deformation that we see at the planetary surface. And here's a wonderful example that we saw from the first flyby. This is the center of the Great Caloric Basin that I showed you earlier. There happens to be 40 kilometer diameter impact craters in the middle. But what is spectacular are the 200 or so radiating troughs that go out for hundreds of kilometers away from this more or less symmetric pattern. And we don't know why they're there. They are pretty much in the center of the caloric basin. Here you see some ideas that people are exploring with quantitative models. But it's telling us that this basin was under extension, it stretched, and it did so in a way that gave rise to very uniform spacing of these troughs, pull-apart troughs that radiate out from the center of this basin. So this kind of structure has a lot to tell us about how the planet deformed over time. Just in the last flyby, we saw one example, albeit small, of stretching that was unrelated to an impact basin. It is these troughs here that continue over here. It's not in the middle of the basin, it's in fact on the top of an elevated block or plateau that maybe got stretched by virtue of some relaxation of the plateau, some expansion of the footprint of the plateau after the forces that produce the plateau stopped operating. It's common on Earth. It has not been seen on other planets. We may be seeing it for the first time at Mercury in these tectonic structures. I want to close with an animation that's put up together by these high-resolution color frames that were taken on the second flyby. We came out of the dark side of the planet as we moved away from the planet. We used all of the filters in the imaging system to put together a color view. Now, there are some artifacts across the whole spread having to do with photometric differences that haven't been illuminated. But flying over this region, simulated, remembering that the colors are enhanced and stretched, gives you a sense for the color variations and how they are related to impact structures, to tectonic structures, to plane structures on the planet. I'll point out a few examples where you see marvelous tectonic structures, a couple of them that run through this big structure. Areas that are relatively blue, areas that are relatively red, and many of them can be tied to aspects of the impact structure. This is a central peak region that is bluer than the orange or red rim material, all different from the brown material surrounding it, indicating that impact structure excavated material of different composition. You see this throughout. Here's a primarily blue or brown area, a big enough crater punches through, and up comes some red material. Here's a lot of blue material that was excavated by an older impact structure. Here's some blue material, but as you get impact craters, you can punch through and see some red. That's your gel. I'm going to close up by saying that the implication of that kind of material, this was a very volcanically active planet. We're seeing kilometers of distinct planes of different color, showing the history of what it is. I'll just close here by saying we only have 3 flybys. We go into orbit in 11 months. When we go into orbit, we're doing the effect of 2 flybys a day. So we've got 730 flybys to go. Stay tuned.